Okay, welcome back. So, what we're going to do today is take a look at motion in one dimension with constant acceleration, and we're going to apply it to problem-solving situations. And in the process of doing that, we're going to take a look at some problem-solving strategies, which could be general problem-solving strategies whenever you have a situation that you can analyze using mathematics, particularly with physics. And if you are taking an introductory physics course, and this is a high school situation, a physics course might be the first place where you really run into these skills for the first time. Some of what we do is going to be a lot like word problems in math classes. But in those cases, the equations are generally supplied to you for which ones are appropriate to use. And part of what physics is that we have to understand enough of the science in order to know what math is appropriate to use for the analysis. And then when we look at our solution, we interpret it again through the lens of the science. You may also have encountered some of this sort of problem solving in chemistry classes if you've taken chemistry prior to taking physics. But in my experience, where I teach, where physics typically is taught after chemistry and biology, this is often the area which is the newest sort of thing for students to work with. So let's take a look here. So in the last few sessions, we took a look at what the definitions of velocity and acceleration mean, as well as displacement. Velocity is the rate of change of position with respect to time. Acceleration is the rate of change of velocity with respect to time. And in the previous video, we derived these three equations that relate the quantities of original and final velocity, acceleration, time, and original and final position to each other. And so there's another one that we're going to derive in a later session and also use. But it turns out that only two of these are independent equations. That is, we could take any two of these three and derive the missing third one if we needed to. So any of our problem solving for solvable problems, we should be able to do with two of these, but since we have a third one there, we might get to a solution faster by one of them, and we'll take a look and see how that applies in a moment. So let's imagine a situation here first where we want to stop a car. So we've got some kind of car, and I'm going to draw a real boxy looking vehicle here, and we want to stop it before it runs into some barrier, some wall. And so we're going to say that this car stops, and we're going to say that before it was stopping, it was going. So why don't we give it some speed to go with to begin with? And how about we say it's going a bit on the fast side? So about let's see, 25 meters per second. Let's make it a little bit easier to do the math straight up. So yeah, sure. Well, okay. So let's say we start off with a velocity of about 30 meters per second. That's around 65 miles an hour. I'd have to check it out to see precisely. I don't have that memorized exactly, but it's pretty speedy. And 70 miles an hour perhaps. So we're going along, we want to stop. And let's say that when we apply the brakes, we have an acceleration that's going in the backwards direction of -8 meters per second per second, meters per second squared. And we're starting at an original position of 0 with an original time of 0. And what we want to know is how long of a distance can we be away from that wall and stop before hitting it. And we also are interested in knowing how long of a time period is it going to be to do the skidding, to stop. So let's take a look first at the problem-solving techniques and take a look at what we've already done here. So when we approach a problem, one of our first things we want to do is we want to draw some sort of picture. This applies beyond just situations with physics. It's often useful to draw some kind of diagram. And it doesn't have to be a direct picture of the physical situation. It could be a diagram that shows, like, I don't know, amounts of energy or something, or percentages of fuel used, or I don't know. There's a whole sorts of things you might use to represent the information that you're given at the beginning and the information you're trying to determine. But getting some sort of visual aid is often helpful. And I said to label the diagram, and along with that, I said list known and unknown variables. And I've kind of combined that in the same step here. So we know that I told you, as we were writing this out, our original velocity is this value, 30 meters per second, and I indicated it there at the original location for our car, and with an arrow representing its direction, and with, because it's a vector quantity, and with the size and the units that go along with it. Units are part of the size properly. I told you the acceleration, and what I didn't specify earlier is that, which we've already done, is that we have chosen a coordinate system. That is, we've selected, by virtue of what things I'm labeling positive and negative, which direction is the positive direction and which direction is the negative direction. So on this problem, the way I've sketched it, everything pointed towards the right of the board is positive, everything towards the left is negative. So that makes acceleration negative since it's going backwards. And to slow it down, to take that energy away, to take that speed away rather, and the original velocity is forwards. Okay, so we've listed those, and we want to think, okay, are there other things that we've stated that we didn't put up there already that may be relevant to this situation? And I said here that it stops. And so we want to think, well, what does that mean? Well, we know that stops means that there's no motion, and there will continue to be no motion beyond that point. And if there's no motion, there's no velocity. So our end condition for the problem is that the velocity is 0. So this tells us that our final velocity gets to be 0. And that's very useful. We like, it's easier to analyze problems when some of the variables that are relevant are zeros. Those terms get to drop out, and it makes the math simpler. Similarly, I've picked situations, I've picked numbers that are arbitrary, and set them equal to 0. When we were talking about frames of reference and choosing origins, we said we had to pick one, but we kept saying, well, you could pick this one or that one or some other one. Here, I'm picking the one that's most mathematically convenient. I'm picking one where the starting position is 0, and everywhere an x sub 0 shows up in any of our equations, it can drop out. And t0 I have also as 0. So anywhere there's a t0 in our equations, that can also drop out. So that makes things simpler for all of our math. Now, we want to consider, are there any other things that we've said that tell us any other information? And I will skip ahead and say, not that's relevant for this particular problem. So, then we want to know, well, what is the relevant physics? That is, what body of knowledge do we have, such as physics, that can connect the things that we know, or at least some of them, to the things that we're looking for? And we know we're looking for position and time, and we have information about velocity and acceleration. And it's a constant acceleration for the entire duration of the problem. And so we have a set of equations. This is our physics here, is the meaning for all these variables that go along with these equations. And so this is like our toolkit that we get to use to apply to solve this problem. So, all right. Now, you might not know which one of these ones to start with. You might have already spotted which one to start with to use to solve for x final or delta t. Let's take a look and see how we could approach this if we were less certain. So, I'll step off camera a moment here to get closer. A technique I like to use is to indicate among all of our equations which variables we know by underlining them. So if I knew I had this set, let's see, we know v final, we know v original, we know acceleration, but we don't know delta t. So I'm going to code that with a single underline everywhere it shows up in any of our equations. Oh, and I notice now that I messed up this equation. Okay. So this is our proper equation. That's our unknown time there. All right. So are there any other unknowns? Well, we know that final position is unknown. I'm going to use 2 underlines for that, wherever that shows up. And so I go and I look through there, and I see, okay, these are our different equations. We know that where our unknowns are. We also know, as a general principle in algebra, in order to solve a system of equations, you need at least as many equations as you have unknown variables. So here we've got one equation and one unknown variable. We can solve for time straight off with this equation. These other two have 2 unknown variables, 2 different unknown variables in them each. And so we're not going to be able to start off with one of these and solve for the thing we're trying to find out, final position, let's say, without either algebraically combining them in some fashion or finding the time first. So let's find the time first. So I'll go ahead and start off and write that equation. And I'm dropping the vector arrow symbols for convenience here for a moment. And we want to isolate our unknown time here. So to do that, we'll divide both sides by A. Doom, doom. We also know that V final is 0 in this case. And so I'm going to go ahead and cancel that. And that leaves us with delta t is negative V0 over A, or delta t I'll just rewrite that here. And so what I usually recommend doing when you're solving these things is that you want to solve them algebraically first before you dump any of your variables in. This is going to help you catch errors. And it's also going to help you see the physics patterns here. That is, this time is going to be longer if the original speed was bigger. The time is going to be shorter if the acceleration is bigger, which we can see just from the math there before we dump numbers in. So let's dump the numbers in. Delta t is negative 30 meters per second over negative 8 meters per second squared. 30 divided by 8, same as 15 divided by 4, 7.5 divided by 2, 3.75. Okay, so there's our answer here is 3.75. And then the units, meters per second cancel. There's 1 power of 1 over seconds in the denominator. So that leaves us with units of seconds. Let's stick that a little further away so we don't think that's a 5 for our time. So yeah, you're going that fast. You have, you think 1, 2, 3, almost 4. It might take a while to actually come to a stop. And that's not an atypical acceleration for, let's say, rubber on dry asphalt. Might be a little higher, but around there. So there you go. All right. Well, now we have the time. Now, now either of these equations will work just fine for finding our unknown final position. So I'm going to pick the top one just because. And so we'll go ahead and write that x final minus x0, which is going to disappear since it's 0, equals v0 delta t plus half a delta t squared. Okay, we already have isolated the unknown we're looking for, our x final. So we can go right ahead and dump our numbers in. That's 8 meters per second times 3.75 seconds plus 1/2, I'm sorry, 30 meters per second, 1/2 times negative 8 meters per second squared times 3.75 squared. Now, seconds. So my ability to square 3.75, I'm less confident in, so I'm going to go ahead and use the calculator just to be more certain. And when we run the math on that, 12.5 meters minus half that, I expect. Yeah. Minus 56.25 meters. So that's going to yield positive 56.25 meters. Okay. And so that can be our answers there. And we can take a look at them and say, well, do they seem reasonable? Do our units agree? Okay, if I stuck in most cases, the units along with the numbers and did the math operations on the units as well. And they gave us units that make sense for time, seconds, and make sense for distance, meters. If I had thrown in the wrong equation, like if I had used this equation and kept it the way it was before with no time and with speed squared up there, then we would have had final answers with units of meters squared per second squared for a distance. And that would tell us that we were wrong. So it's useful sometimes to do the math on the units. It can help you catch some careless errors, like the one that I made at the beginning of the video. So there we go. And I'm going to go ahead and stop this video here. And the next one we'll talk about free fall and work a problem with that.